Let's talk about the continuity of piecewise functions. So at the top of the page here, I have just a reminder of the definition of a function f of x being continuous at some particular x value a. It would just be that the limit of that function as x approaches a equals f of a. So essentially what this means is that at that number, the limit equals the y value. So there's no jumps, holes, vertical asymptotes, no funny business, right? The limit exists from both sides. The y value exists, and it's not in some random far away place. It is the same as the limit. Okay, so we've already talked about continuity of like regular functions, and it was really helpful with us like being able to compute particular limits. But when we apply this definition to problems that use piecewise functions, like you can see here, things get a little bit more complicated. But it all comes back to this original definition. Okay, so let's talk about this first example. So f of x is this piecewise defined function. And you can see there's one kind of mystery piece of this definition, which is the letter C right here. So this is kind of the unknown fixed number. Unknown number, right? So it's not like the input variable of the function or anything, that's x. This is just kind of like what the question is going to ask about. So the question we're being asked here is for what value of that C is f continuous at -3? So if we look back at the split of this piecewise function, we can see this is not a piecewise split that we see very often, but it is possible. So what this is telling you is that you're using this formula for any x value that isn't -3. So so to the left of -3 and to the right, so less than and greater. And then right at -3, you get this number instead. Okay, so -3 is kind of like the one jump point of the function. So we know that, especially built this way, it's very, very possible that we have something like this going on, where there's, a limit being created by this function, and then a y value being set kind of somewhere else. So if it's going to be continuous there, we would have to find exactly the y value of that missing point and put the dot at that number C. So to be continuous at 3, we would need the limit of this function as x approaches -3. We need that to equal f of -3, just using the definition of continuity. All right, so f of -3 in this problem is just whatever C is, like that's the number being assigned to it. And this limit, because it's not using -3 itself, it's just all the points around it, this limit is exclusively using this function. So this is the limit as x approaches -3 of this formula. So if I can compute this limit, that number, if this does come out to equal a number, is what I want to be equal to C. So I need to compute this limit. So x is approaching a number. So my first attempt is to just plug the number in and see what happens. And this computation isn't great. But if you fight through it, you should find that it's 0/0, which tells me this is probably a hole in the graph. So because I'm looking at polynomials, I'm going to factor them and hope for an x plus 3 to cancel top and bottom. All right, so on top here, x squared minus 2x minus 15 factors to x minus 5x plus 3. In the denominator, I can pull an x squared out of both of them, and I get x plus 3. And sure enough, top and bottom, there are my x plus 3s. So that's what's actually creating the 0/0. So I can take them out for the limit, and now I can just plug in -3. -3 minus 5 over -3 squared. That's -8 over +9. So I need -8/9 to equal C. So that's my answer. As long as we set this number to be -8/9, it will perfectly fill in the hole in the graph that's been created. All right, let's look at one more example in this video. So this one is using an A instead of a C, but sort of in a similar way. So we have a new piecewise defined function. X is the input variable. So this A right here is just kind of another like unknown constant number. And that's what the question is going to ask about. So we have this formula for X less than 1, this formula for X greater than or equal to 1. And the question is for what value of that A, so what number there, makes F continuous on minus infinity to infinity. So this is almost the same question overall, even though the setup is different. So this one, we were only concerned at -3, and here we're concerned about it being continuous everywhere. But the key here is that no matter what number A is, this is a polynomial, which is always continuous everywhere, no problems. And so is this. This is a straight line, but that's a type of polynomial, degree 1. So both of these are just continuous absolutely everywhere. So the only thing that could make this function not continuous everywhere is right at +1 when we switch from this graph to this graph. We might have some sort of jump that creates a discontinuity. So what we want to do is make them kind of set A so that they meet up in the same place, right? Like one leaves off and the other one just picks up and keep going. Then you don't have any discontinuity. Yeah, so again, to be continuous at 1, we would need the limit as X approaches 1 to equal F of 1. Okay, and this one we're going to kind of split up differently. So the other one, the limit as we approach the number from both sides was using this formula. But now the limit from the left uses this formula. The limit from the right uses this one. So I actually need to split this up. So I need the limit as X approaches 1 from the left to equal the limit as X approaches 1 from the right to equal F of 1, right? If all of this is true separately, because I'll have to compute them separately, then these are equal to that limit and everything should kind of match up the way that we want it. Okay, so this limit right here, the limit as we approach 1 just from the left side, is going to use only this function here. So this will be limit as X approaches 1 of X squared plus AX. So right now, we don't know what A is, but whatever it is, this is a polynomial. So this is the type of limit where you can just plug in 1 to compute. So we would get 1 squared plus whatever A is times 1. So that's 1 plus A. That's as far as we can get it without knowing A. So we'll move on to the next piece here. And I want you to notice as well, the limit as X approaches 1 from the right is going to use this function. And in fact, these two are automatically equal because at X equals 1, you're using this function because this is X greater than or equal to 1. So both of these will be equal to, I'll write it as a limit for one more step, but it's really just 3x plus 5 with a 1 plugged in. Both of those are going to be this value. So we have 3 plus 1 is 8. Or sorry, 3 plus 5 is 8. Okay, so what we need is for this limit to equal this stuff. So now I just need to set these two guys equal and solve for the A value that makes it happen. So I need 1 plus A to equal 8, which tells me the value of A should be 7.